No one ever imagined that one day the secret of an atom would be hidden within the colors of the flame. But someone did. Years later, Niels Bohr would look back and say, "In 1913, almost no one believed that these colors had any meaning, because those colors that looked random, like the patterns on a butterfly's wings, beautiful but meaningless, until someone realized those patterns were actually a code." February 1913, a 27-year-old, isolated, overlooked physicist staring at a formula. And in that moment, one of the smallest building blocks of the universe began for the first time to truly be understood. This was not just a discovery. It was a leap that rewrote the rules of physics. Niels Bohr once said later in his life, "Back in 1913, almost no one believed that the colors of light emitted by burning hydrogen, despite following a pattern, could reveal anything meaningful about physics. To him, it was like the color patterns on a butterfly's wings. No one would think that the colors on a butterfly's wings could lead to the foundations of biology." But in February 1913, 27-year-old Niels Bohr read a book about the spectral lines of hydrogen. And suddenly, everything clicked into place. Within just a few weeks, he wrote a paper that would fundamentally change physics. Are you ready for the story? Let's begin. I want to begin the story 2 years earlier, September 1911. At the age of 25, Niels Bohr travels to Cambridge. He is so excited that in a letter to his fiancée, Margrethe Bohr, he writes that when he saw the word Cambridge above the door, he was overcome with joy. Bohr is thrilled at the thought of working with the extraordinary J.J. Thomson, the man who discovered the electron 14 years earlier, and with his impressive students. But things do not go as he expected. Everything turns into a complete disappointment. The students have no interest in speaking with the young Danish man who mutters to himself and has strange ideas. Worse still, his relationship with Thomson begins badly from the very first day. Because on that first day, Bohr picks up Thomson's book, opens it, and says to the Nobel Prize-winning scientist in his broken English, "This is wrong." Bohr believes the conversation went well, but within a few weeks it becomes clear that it did not. He writes to his brother Harold Bohr, "J.J. Thomson is not as easygoing as I thought on the first day. He hasn't yet had time to read my paper, and I don't know whether he will accept my criticism." For the next 3 months, Niels Bohr is unhappy. Most of the time, he is alone. On December 6, 1911, his life changes. J.J. Thomson hosts an annual dinner for his students. It is quite a peculiar event, formal attire, 10-course meals. Yet at the same time, people climb onto tables and sing songs about physics. Yes, physicists were strange even back then. For dessert, plum pudding is served. This is a subtle physics joke because Thomson's atomic model is known as the plum pudding model. Electrons are like raisins scattered within a positively charged pudding. But the joke is also somewhat controversial, because among the guests is a former student, Ernest Rutherford, and just 9 months earlier, Rutherford had proposed a completely different model of the atom. At that time, Ernest Rutherford was only 40 years old, and yet he had already discovered alpha and beta radiation, defined the concept of half-life, developed a method to estimate the age of the Earth, demonstrated that radioactivity can change the atomic number of an element, And most importantly, he realized that alpha particles could bounce back from a thin metal foil. This discovery suggested that J.J. Thomson's model might be wrong. According to Rutherford, most of the atom's mass must be concentrated in an extremely small nucleus. In his 1911 paper, he described the atom as a dense positive charge at the center, surrounded by negatively charged particles distributed around it. But this model did not gain much attention, because most of the atom appeared to be empty space. The nucleus was unbelievably small, and the biggest problem, why don't electrons fall into the nucleus? According to classical physics, electrons should radiate energy as they move and quickly collapse into the nucleus. In other words, Rutherford's atom, by its own rules, seemed unstable, almost doomed to collapse. In Cambridge, almost no one believed in this model, but years later, Niels Bohr would describe that moment like this. Yes, I was the only one who reacted to it, but in truth, I did not react. I simply believed. At that dinner, Bohr realizes something important. He is working with the wrong person. The right person is Ernest Rutherford. Rutherford is an energetic and inspiring scientist. Bohr asks J.J. Thomson for permission and leaves for Manchester. In 1912, he begins working in Rutherford's laboratory. He later describes those days as, "I am working joyfully, inspired by a great man, in a laboratory filled with people from all over the world." But Bohr soon realizes that experimental work is not for him. He tells Rutherford that he wants to focus on theoretical work. Rutherford does not particularly like theorists, but he makes an exception for Bohr because he finds him exceptionally intelligent, and he is a good football player. Yes, that helps too. At the Solvay Conference 1911, it had become clear that the idea of quantum theory was here to stay. Max Planck and Albert Einstein had already introduced this idea, but no one knew how to apply it to atoms. Even Einstein himself said that these ideas could drive a person mad. But Niels Bohr thinks differently. Classical physics is not sufficient to explain the atom. Quantum theory is necessary. In 1912, Bohr returns to Denmark and marries Margrethe Bohr. Margrethe plays an extremely important role in his life. Bohr dictates his papers to her, and Margrethe edits them. In fact, for years, nothing is published without her approval. But his work reaches a dead end for a while. Until February 1913, a colleague asks him a simple question. How does this theory match the spectral lines of hydrogen? Bohr is surprised. He has completely forgotten this formula. In 1885, Johann Balmer discovered that the frequencies of light emitted by hydrogen follow a precise mathematical pattern. When Niels Bohr read this, he later said, "The moment I saw Balmer's formula, everything became clear." In just 4 weeks, Bohr wrote one of the most important papers in the history of physics. In this paper, he proposed that electrons can exist only in certain discrete orbits. He called the lowest energy state the ground state. And most surprisingly, he solved the biggest problem. He assumed that electrons do not radiate energy. Yes, he simply assumed it. This was one of the boldest assumptions in the history of physics. In addition, he proposed that energy is quantized. he showed that electrons can occupy only specific energy levels. And the most radical idea was this: light does not come from the continuous energy of an electron, but from jumps between energy levels. Even Albert Einstein could not hide his astonishment when he heard this idea. Niels Bohr's model explains the hydrogen spectrum, derives the Rydberg constant. It even explains the Pickering series, showing that these lines actually originate from ionized helium. In 1913, Bohr sends his paper to Ernest Rutherford. Rutherford responds, "Your ideas are very clever, but the mixture of quantum theory and classical physics is difficult to understand." When the paper is published, some consider him mad, others admire him deeply. Albert Einstein says, "If it is correct, it is of great importance," and later adds, "Bohr's theory was a miracle." And this theory is not perfect, but it opened a path, and it introduced a fundamental idea that is still used today. Energy changes produce light. In 1927, Bohr reaches a profound conclusion. You cannot ask what an electron is. You can only ask what you can measure. This approach becomes known as the Copenhagen interpretation. Einstein strongly opposes this idea, and thus begin the historic debates between Bohr and Einstein. Thanks for watching. See you in the next story.